Now, before I go into the lecture this time, let's actually take a look at the homework so you know what's ahead of you and where we're going with this. So I think instead of talking about each of these problems, this is a warm-up problem, this is a warm-up problem, it comes down to these two problems here. And let me use the one here on the top, problem C, as a introduction of where we're going with all this. So what you see here is a plate that has an edge length of 3 feet and 3 feet on the bottom. And then we have a random edge here. And that random edge is defined by a function, x squared over 3. And right now we don't care about the function, but what I need you to understand is that this entire plate here has a support reaction at A and one at B. And it wants to, of course, fall down under gravity. And how does it want to do that? There's actually what's called the centroid in a geometric sense, or the center of gravity in a physical sense. And I pretend for a second that's right here in the plate. That's obviously not correct. It's not to scale, but you probably will understand that gravity wants to take the entire weight of the plate and push it down in this direction, or pull it down in that direction. And so once you would know what the force of the plate is, so I'm going to call that force plate, and you were to know the distance that the centroid location, or the center of gravity in this case, has to the y-axis, right? Let's call this here x bar for now. Then I could actually calculate all my support reactions. And not that you need to fully understand this right now, but where we're going is we obviously have a tensile force here, and therefore we must have a support reaction here that goes in this direction. And we also must have a support reaction that goes up here. And I can already tell you that this upwards is of course equal to the total weight of the plate, because the only thing that goes down is the plate, and this is going up. But again, this is not about numerical values here. This is only about the concept. So this would be equal to that. And now you probably understand that if I take the sum of the moments about point A, the two things that have a lever arm would be what I call RBX and also F plate. And so to calculate RBY, I would just set up an equation that says the sum of the moments about point A is equal to 0, and 0 is equal to RBX multiplied by 3 feet. That's the lever arm, and that actually happens to rotate counterclockwise, so therefore I'm going to make that positive. And now I have my F plate, and maybe I use red for that, F plate multiplied by what I called X bar. And that rotates clockwise, therefore that is negative. And now you can solve technically for RBY, right? So you could solve for this value. And what you need to know, or the one thing that you at this point in the class do not know yet, is actually what is the weight of the plate, although you probably could calculate that yourself if you know the area. But what's brand new here is how do you get this value? So this is really the focus of today's lecture. How do I get X bar? And that is the distance between the centroid of the plate, right? So I'm going to call that here C for centroid of the plate, to the origin, right? So the origin is down here, O. And that is really the goal of today's lecture, to understand how can we calculate the X bar. And then as a bonus, we also will talk about how to calculate the weight of the plate, although you probably know this technically from classes you have taken before. Why? Because ultimately our goal is to find support reactions for systems like the one shown here. So that is the introduction to why we're doing what we're doing. So now let us move on, and let's first talk from a very high level.